All right, a short review of what we did last time, so hopefully you know where we're coming from. We had a structure, used to be a simply supported beam. The stresses in it at 60 feet were so horrible that they decided to put some intermediate supports in there. They put one at B and one at C. By adding extra supports, they made it statically indeterminate, +1, +1. And therefore, we cannot determine the forces or the shear moment diagram by statics alone. This particular structure has the potential, whether used or not, to resist in five points: A horizontal, A vertical, roller, roller, roller. There's 5 unknowns. You have been given 3 equations of statics. So we decided to turn the real structure into something that we can analyze by statics, even though it probably will not behave the way we want to. This is called a primary structure. It has several other names. It is simply the original structure with enough supports removed such that it is still stable and statically determinate. Now you need to remove 2 forces to get back to a statically determinate structure. If you decide to remove B vertical and A horizontal, that will not work because the A horizontal is necessary to keep it from rolling horizontally to the right and to the left. So instead you take off these 2 reactions, or you could take off this one and this one, or you could take off that one and that one, or you could take off the 2 we did, or you could take off the 2 outside ones, or you could take off these 2. They'll all work. Yes, sir. It is usually easier visually and conceptually to see what's happening and to get the answers, yes. But that doesn't make a lot of difference. You're welcome to take anything, a little bit of thought, and it'll work out just as well. All right, so we took the original structure, turned it into a primary structure, put the real loads on it. Who knows, we may get lucky. The structure may deform just like we want it to. That pushes that down. Therefore, it has a slope like this on this end, but I'm going to have to get rid of that slope and get it back down to point C. And then I notice that that's got to be attached at D, so that's probably how the structure truly deflects. And when I look at the deflections of my primary structure, or I think he calls it a base structure, that doesn't look like that's very likely to happen. Looks like these deflections will be induced in the primary structure, and they're not supposed to be there. So I draw a moment diagram for the real structure. You can write an equation for this range. It would be 333 times x minus 2 times x over 2. We already discussed that. You should be able to write an equation for moments in any range. Or you can use volume integrals, in which case, rather than having to write an equation for the range and then multiply that equation times another moment equation and integrate from 0 to 20 and then do this range in here separately, you can just use the volume integrals, which is what I chose to do. I looked at the table of volume integrals. And notice that parabolas in general require a value on the end, a value in the middle, and a value on the end, and therefore that's how many I went for immediately. I drew a free body and solved for the moment at the end. Then I cut it at the middle and solved for the moment in the middle. Then I cut it at the end and solved for the moment at the end. Those are the 3 values called for in the volume integral tables. Then, in order to solve for the deflection at B, sub 0 we use for the real loads. I'll put a unit load where? Dietz. At where? At B. Boy, you're so lucky. I tell you. You know, when your fingers are doing this, everybody knows what you're doing. All right, that is correct. To solve for the deflection at B, you would put a unit load at B and you would draw a moment diagram M sub Q for the Q set, where you already have the moment diagram for the real load set, and you would integrate M dx over EI. Or you would volume integral this guy combined with this guy, plus, even though there is another line dropped here because we're going to be looking for something there, this is one continuous triangle combined with one continuous triangle, and so we don't have to stop in the middle. And this is what we had last time. We were going to use the volume integrals to combine a parabola with these three values with a triangle with the fat end of the triangle on the right end of the parabola, plus, and those were over a 20-foot length, plus two 40-foot triangles of values shown. And we got this equation out of the volume integrals, and we wrote these numbers down, and I went on and cranked that out. This number comes out 32,592 over EI plus 47,408. You can check it. It may be wrong. I'm going to pretend it's right regardless. Turned out to be 80,000 over EI. That is the deflection at point B due to the real loads. Next, now incidentally, what I actually did is I didn't crank this out on a calculator, and I really never do. I don't even write this down, although that comes out of the volume integral table. What I do is I just look at this and this on that volume integral table, and I go get the computer to do it for me. This is, if you go to the syllabus, if you go down to volume integrals, this was a .xls file, and all it does is give you all the different shapes that I knew about when I set this up, and you pick the one you want. So if you want a parabola with a triangle with a fat end on the right, you go to a parabola and a triangle with a fat end on the right, and there's your number right there. I was obviously doing something else at this time. You put in the length here. If it calls for an L1 and an L2, this one here calls for an L1 and an L2, put them in. If it calls for an L3 and an L4, you put them in. This is A, B, C, D, and E. In my case, all I did was put in C, D, and E. I put in C, D, that's why I'm getting 0, and E. And for the triangle, I need L and A, so I put in L and I put in A. When I put in those numbers, the answer showed right there. Now, sadly, you don't get to use that on a quiz because, you don't have access to it. You'll have to do it this way. But for stuff you're doing for your homework, I think that's pretty handy. Well, no, not really. Because if I know you, you'll have a PDF of the text and the old quizzes and the... All right. Now, the next thing you should have in your notes, I assume you're probably printing these out, looking at them. We were required to solve for the deflection at B due to the real loads. We just did that. And we were going to solve for the deflection at B due to B vertical. rather than go ahead and get the whole thing now, I'm just going to put a unit load there, and then we'll multiply that times B vertical when we set up our equations. And so we wrote down our phony dummy virtual loads along with our real loads. This would be B vertical if we did the whole thing at once, but it's really convenient just to do a 1 for right now. 1 kip. And we drew moment diagrams to go with them. They're obviously both the same. No, they're not the same, because this is, yeah, they're the same. That's right. I was thinking this was this height. This is the reaction due to the 1. This is the reaction due to the 1. This is 13.33. This is 13.33. And then we combine this guy with this guy and this one with this one using our volume integrals. And I wrote down, I said this plus this and this is equal to known. When I went, yes, sir. And if you got a question, holler, because I'm going to rattle on here. I'm having fun. Getman?
What if the moment diagram is negative?
Oh, then perfect. In other words, if this one's above and this one's below, then you combine a positive area with a negative area, and it comes out a minus sign.
So, but you still, for the volume integrals, you still use the same?
Well, they'll still show above, but see, this value will be a plus 13. This value will be a minus 13. So actually, when you put the number in, it'll come out minus.
So it's just the sign that changes, right?
That's correct.
Because I was thinking maybe if it's the same area above and below, it would turn out to be 0.
Oh, no, never. Won't turn out to be 0.
Yeah.
In other words, if I hand you a piece of wood that's been cut in any shape you like, the volume is positive. Now, in other words, the resulting answer here may be negative, but the volume itself would be a positive. Yes, sir.
If you had a beam that caused a moment to switch signs in the middle, you just cut to that point and then sum them two, right?
It depends. I don't think the volume integrals that I gave you have that much meat on them. See, they don't. But the volume integrals that this guy gave us actually has one like that, where it goes above and below, and here's one above and below, and here's some that are above and below. They're just volumes is all they are. So you can use these. Although you could just go, like you say, just go to where it hits the 0 point and get that volume, and then go from there on and get the remaining volumes. That'll work also. All right, now the answer for that delta BB, this one right here turned out to be 1185. This 40 by 40 at 13.33, when I put it in the computer, turned out to be 2370 for a total of 350.55.6. Then I said the next thing we would need to do would be to solve for the deflection at C, because you put a load at a reaction at B, or a load at B. And that would require you to combine those things right there. And I don't think we bothered doing it. I figured you could do it just like anything else. And I'm not going to rewrite it all down. I'll just tell you it'll be on page 3A in the notes when I post them. But basically, this was 30 feet. This was 30 feet, and this one was 30 feet. The first one was 20 feet. It's not drawn very well to scale. And 10 feet. And this reaction, this was a 1. And this reaction was a 0. Let's see, it's in the middle, so it'll be 0.500, and the reaction is 0.500. Here's when the load was at the 20-foot mark, and, well, that's 10, and that's 30. And this reaction for the 1, that would be 40 out of 60, so that would be 0.667 and 0.333. And so you multiply 0.5 times 20 and you get the height. and the height of this particular moment diagram, half of 20 is 10, and 0.5 times 30 is 15 for the moment diagram height. This is a 1 kip load causing this. And this is 0.667 times 20. Let me cheat. There's the 10, there's the 10 and the 15, there's the 15 going down. On this one goes up to 13.33. This is due to, yeah, that's right. 0.667 times 2 is 1.333, and so it's times 20 is 13.33. So this height right here is 13.33. Again, there's nothing but moment diagrams here, and you've really got to be able to do them. And this one right here would be 0.333 times 30, and that comes out 10. And so you're going to combine this guy, you can integrate it if you like, with this guy. Then you're going to use a volume integral this one with this one. And then you're going to use a volume integral this one with this one. So this is a 0, 10, 15, 0, 0, 10, 15, back to 0. And on the other one, it goes up to 13, 0, 13, 10, 0, 0, 13, 10, back to 0. And so I just stuck those in the computer. I asked him if I got two triangles, both facing the same way, what is the volume? And he told me. And then I said, how about a trapezoid? Little n, big N, little n. And he told me. And I asked him two triangles facing the same way. He says, I just told you. I said, no, I got new numbers. It's 30 feet long instead of 20 feet long, and it's got different heights. He says 1,500. That is delta at C because you put a unit load at B. Now then, here is this reciprocal law that we talked about. Turns out that if you put a unit load, or you put any kind of a load, let me find the original structure would be best. Turns out if you put any kind of a load at this point, it causes a deflection over here. And if you put a load at this point, it will cause a deflection over here. And that reciprocal law, look it up, says that if you multiply the loads you put here times the deflection here caused by this guy, it has to equal to this load here times this deflection caused by this guy. If you change those to ones, that says that delta CB has to equal to the deflection at B due to C. In other words, a unit load here causes a deflection over here, and a unit load here causes a deflection over here. This load times the deflection caused by the other guy is equal to this load times the deflection caused by the other guy. So 1 times delta BC, because of the other guy, will equal to 1 times the deflection at C because of a load at the other place. Basically, it means you don't have to do any more work on this one. Delta BC is equal to delta CB. And if you don't believe that, watch this. This is the moments due to the Q loads, And these are the moments due to the P loads. This was due to a unit load at B. This was due to a unit load at B. If you'll draw the moment diagrams in reverse, put this one here and put that one there. Howdy. Flip-flops always get you in trouble when you come in late. You know, tinnies are good, but flip-flops make a heck of a racket. You're going to get the same answer. In other words, pick up this one due to the Q load and move it over here, and then pick up this one and move it over there. You have exactly the same two moment diagrams. So you don't have any choice but for delta BC to equal to delta CB. And the last thing we need, I don't know if it's the last thing, we need the deflection at C because of a unit load at C. Here's the real load in the middle, and here's the phony load in the middle. And that means that you're going to combine his moment diagram with his moment diagram. And both of them are the same. Here's 0.5 times 30 will be 15 and 15, and his will be the same, so there'll be two of them, and you get 4,500 over EI. Now you can check any of these numbers and make sure you get the same thing. You ought to. If you don't, two possibilities. You still don't know what I'm doing, or I don't know what I'm doing. If you find out it's the latter, tell me and I'll change my numbers. The final thing I need is, back to the original structure, I need the real deflection due to the real load at B and at C. And then I'm going to need to know that same deflected shape with B vertical, the reaction only on it. There'll be two deflections I need to know about. And then take that load off, and the real load's off, and put the reaction at C on there. And there'll be two deflections I need to know about. The last one I don't have is this guy right here. How much deflection at C do you get due to the real loads? We didn't do it because we figured, you know, it's just like everything else. But here it is. Where is it? Got to be here somewhere because I got a number for it. There we go. There we go. The deflection at C due to the real loads. Again, to get that, I draw the primary structure with the real loads on it, and I get a moment diagram due to the real loads. Then I draw the primary structure with a unit load in the direction that I want to know the deflection. And that is the M sub P. And if you would like to write equations for these things, you're welcome to do so. Had somebody in my office a while ago was integrating it. I think he said it would, I don't remember what he said. It was clean, pure, something, you know, he's obviously a product of Math 151. Not much I can do about that. But it takes a while, I really tell you, because you gotta write these equations carefully and then integrate them. Anyway, here I combined region 1 with region 1. I then combined region 2 with region 2, drawing the moment diagrams. That is not M sub P. That's the load diagram, and it causes M sub Q. Not only had the wrong name, it was on the wrong diagram. This is the real load. This is the moment diagram due to the real load. This is the unit load at the point you want to know the deflection, in the direction you think the deflection goes. And here's M sub Q for it. Is there anybody else out there? No? You're the last one? I don't believe it. So here's region 1's number. Here's region 2's number. Here's region 3's number. Now, if I give you a hard time for coming in late, then, and you don't, can't stand it, well, then just tell me. When you come in, just do this, and I won't pick on you. Or wear a hat like that back there. Because I'd rather you come late, even if, everybody else needs to be woke up around here, and you just happen to be a good way to wake everybody up. Is equal to, there's the deflection due to the real loads at point C. So now here's a summary of what we have found. The real structure with the real reactions still applied, which we can't solve because we don't have enough equations, looks like this. There's a reaction at A, pick a direction of your choice, and a reaction at D, pick a direction of your choice. I'm pretty sure one of these is wrong. I can care less. I just put both of these reactions as down because that way I'll put all my unit loads down and be able to solve for the deflections, and I think they'll be down. It is equal to 2 kips per foot spread across the beam. It causes a delta B0, which you and I now have a number for. Wasn't easy, but we got it. And it also causes deflection at C due to the real loads. Superimpose upon that the right answer for the reaction at B. I'm assuming that it goes down. If you come out with a minus sign, that means I guessed it wrong. The reaction at B causes a deflection at B. And its magnitude is delta BB. And you say, no, that's not right. Delta BB is only 1 kip big. You're right, I forgot. That's only for 1 kip. Multiply it times R sub B to find the total deflection that this number causes at B in the downward direction. And that reaction also causes some deflection at C. I mistakenly wrote down delta at C because of a unit load at B. And you said, there's not a unit load at B. There's a big old reaction at B. And so I multiplied what you got, delta CB, times R sub B. And then I did the same thing when I put R sub C. The final answer is what this says. This is equal to, big time equal to, this plus this plus this. And in equation form it says delta B0 plus this guy equals, where did the beam end up after all was said and done? It ended up at 0. And therefore delta B0 plus R sub B delta BB plus R at C delta at B due to C is equal to 0. Second equation says the same thing for C. Plug in our numbers. 80,000 plus R sub B times the number we got plus R sub C times the number we got. You'll notice how this number is the same as that number. And you solve those two equations simultaneously. That's about as far as I got before class began. My guess is your calculator will probably solve that. Will? Okay. TI 85? Will an 85 do it? Never seen one, huh? Well, that's how old you get. All right. So this is what I used. I used those volume integrals. This is a more complete set. For example, he's pretty nifty. He's got a cubic. The only thing on these, it's a little difficult to tell exactly what he means. So I'll just tell you that he means this is the beam. The beam is that long. If he calls for a value M, he's talking about in the middle, that's L over 2. If he calls for a value R, it's how far it is from the left end of the beam to the point you're talking about. And these are like percents. In other words, all of these numbers, he didn't multiply any of them times L. He says all I did was integrate g, a function of x, plus g, a function of x, m1, m2, dx. I didn't put in the EI, and I also didn't go from 0 to L. I went from 0 to 1. It looks like an L, but it's really a 1. So you'll have to multiply all of these times L. And for example, right here he calls for 2 minus R. R is this distance right here. R is how far it is from the left end of the beam to the peak. And if your beam is 60 feet long and this is 10 feet long, then R is 10 out of 60. That way he doesn't have to have, like a lot of mine say, L1 and L2 and all that kind of stuff. He works them on like a percent basis. And from the right-hand end, that is T. And it does get a little hard to see them, but for instance here it says AC onto 1 plus 1 minus T onto 2 minus T, paren close, divided by 12. So get a magnifying glass if you really want one of these. Some of them are really pretty nice, like here's a 3rd degree. I haven't seen any of them with a 3rd degree on there. So here is my problem. My problem is I have a frame. It is 12 feet tall and 10 feet wide, and it has a load on it, triangularly distributed. Wind a lot of times will do that, from the bottom to the top. The frame is fixed on the left-hand end and it is fixed on the right-hand end. As such, it has 1, 2, 3, 4, 5, 6 reactions, and that means it is statically indeterminate to the 3rd degree. In order to analyze this structure, you're going to have to take loose 3 reactions, and when you do that, you can't make it unstable. So for example, this structure right here wouldn't work, because you took off both of the horizontal forces that will help it sit still when you put the load on it. And you took loose 1, 2, you actually took loose 3, you actually took loose 4 unknowns there. That's too many anyway. Now, I wrote this down just for scratch paper for me, because the other thing is stuff you already had in your notes, basically. So let me redraw it so you have time to redraw it and think about it. Here's the real structure. It's fixed on the left. It's fixed on the right. It has a real load on the real structure. The real load is 2 kips per foot. It's 10 feet wide, 10 feet tall. Now most, yes sir? Was it 12 before? Thank you. Yeah. We haven't really done anything, so it doesn't matter, but I didn't want a 10 and a 10. Give me 2 different numbers so you know when there's a 12 showing up and a 10 showing up. Now, that needed to be said, but what was I thinking? I don't know. I guess it'll come to me. It is statically indeterminate, as we said, to the 3rd degree, so I'm going to release 3 supports. Oh, I remember. In the book, the problems don't get too complicated, so we can almost always use names like the deflection at B due to the real loads. Usually he'll give that one a big delta to kind of emphasize the fact it's due to the real loads. Or he can use the deflection at B due to a unit load at A. If they get a little ugly, he might say the deflection at B horizontal due to a load at A in the vertical direction. Those subscripts, they get out of hand in a hurry, especially when you have a lot of unknowns. So I'm going to tell you that I have a 1, a 2, and a 3. That way, when I want to know the deflection in the number 2 direction, because someone put a number 3 type of load at this point in that direction, all I got to do is call it delta 2, 3. You can always go back and see which one we're talking about. Now this is equal to the following. It's equal to that. Now, believe it or not, this is really critical that you see what's going on here. I'm going to now draw the deflected structure. With any luck at all, I won't make any mistakes because I'm not going to be able to erase them. It deflects like that. And then because this is a right angle, it deflects like that. And then because that's a right angle, it deflects like that. Now, for all I know, this point may go to the left. I don't know, and what's more, I don't care. I'm going to tell you that this point moves some direction, some amount. And that amount is what you and I will call the deflection in the number 2 direction due to the real loads. And I think it probably does go down, but I don't care about that either. What's his name? Where's my list? See who's awake. Gee, if I can't find my list, I'm dead. There's my list. Delta 1, 0. Exactly correct. It's the deflection in the number 1 direction. I'll give it a big delta because it's due to the real loads in the number 1 direction due to the real loads. And finally, you have some rotation. It's actually a theta. Its answer will come out in radians. But it's still called a deflection in the number 3 direction due to the real loads. 2 of those will come out in inches. 1 of them will come out in radians.
Instead of the delta 3 knot, can you use
Nope.
delta 1 knot?
Nope.
Or
Nope.
2?
Nope. 8. Nope. Nothing but this.
Well, isn't it enough just to say that it moves in the x direction and the y
Nope.
direction?
Because you see how you've restrained the rotation of this point? I'm going to have to come in. When you get through pushing it up and pushing it to the right, you'll probably be able to make it go back to here. But sadly, it'll have an angle on it. And you'll have to come in with a third force, a moment, to twist that slope out of there. And not only that, by about the time you twist that slope out of there, dang thing going to move up in the air and to the right. And so you're going to have to jockey all 3 of those numbers around until they perfectly combine to give you a beam that doesn't move up or down, doesn't move left and right, and doesn't rotate. Namely, the final product will look like this, come out like this, will come out like this, will come out like that, probably will go down here and come up there like that. Now, I don't know exactly what it's going to look like any place, but two places. Got to come straight up, got to come x equals 0 and y equals 0. Got to come straight out, x equals 0, y equals 0. Nothing else will be my structure. All right. Now, with this thing is a moment diagram. And the moment diagram is going to have what shape on this vertical piece? Your finger knows the answer. Now see if we can get it into... parabolic is a good first guess. However, the load is x to the 1, so the shear will be x to the 2. And so it's not bad. It's better than no guess at all. That's what I got out of most everybody. It's a cubic. And so before I even get started, I might as well go find out what a cubic would do to me. What would the guy call for a cubic? Well, I already know my notes don't have it. Here's a cubic right here. He says I can tell you all of the volumes combined with triangles, trapezoids, these goofy things, triangles with a value in the middle, parabolas, and golly, you put the easiest one last. He says I can do all of those. You're going to have to tell me the value on the end, at the third point, and at the end. There's where I need my numbers, right there. And so the first thing I'll do on a 12-foot beam, I'm going to come down here 4 feet, and I'm going to draw a free body, and I'm going to find you the answer for the moment. And I already know the answer on this end. What's the answer on the end?
0.
Right. And you all may have said that too, and I just didn't hear you. If you'll cut this piece of the beam off to the right, you'll find that there's no load over there, and therefore the answer for the moment at this corner is 0. Now then, here is this top piece. That's 2 kips. You know what? If you don't mind, because you don't mind, because we haven't done anything with it yet, I'm going to change that to 3 kips per foot. And I don't have that anywhere else in the notes. It's a 3 kip per foot load. And the reason I want to do that, it makes my number work come out easier. This is 3 kips per foot. You go down here 4 feet. You cut the beam at the 4 foot mark. Here's the beam. Comes on over like that. Comes on down like that. It's cut at the 4 foot mark. 3 kips per foot. What is the load 4 feet down? 2. That's right. That's why I like that number. Rather than being 2.333 or some goofy number like that, it's 2 kips per foot. I can then solve for the moment at this point. It's an arbitrary thing, but I got to decide before I get too far into this, what am I going to call positive moments? And I don't know. Let's say if they go this way on the beam, they're called positive moments. Because if that was rotated, that would be compression on the top. But that's a positive moment now. And this is the moment, what we're going to say, at the 4 foot mark. And it will be due to 2 things. It'll be due to a triangle, and it will be due to a rectangle. And here's the centroid of the triangle, and there's the centroid of the rectangle. And because if you're going to call that a positive moment, then the moment at the 4 foot mark, this is, let me write it up here somewhere. compression on the outside it doesn't matter, which is one of the problems, is because it doesn't matter. But you have to be consistent. When you start putting all these other goofy loads on there and unit loads and stuff like that, you have to agree with this guy's positive sign convention. Compression on the outside is equal to positive moment anywhere in the frame. Okay, there's our sign convention for this problem. All right, now the moment at the 4 foot mark, you'd say caused by this triangle. This is 2, so there's 1 left over here. That's 1 kip per foot. Let's see, that's going to be a minus 1 kip per foot times the base, 4 feet, times 1/2 because it's a triangle. What I have written down so far is the load under the triangle. Now I'll use a different symbol for a moment arm just to keep it separate from the load. This is the load, this is the moment arm. What's the moment arm? Darn, still came out a goofy number. Too late to worry about it now. 2/3 of 4. That's the moment arm. Minus, due to the rectangle, it's 2 kips per foot tall. It is 4 feet wide. And there's no half because it's not a triangle. And the distance to the centroid is 2 feet. And so there's the moment at the 4 foot mark. Turns out to be a negative number, meaning that these loads do not cause compression on the outside of this frame for this problem. Then the next thing I will need, here is that, let me get this out of the way because I got too many numbers in the way. Here is that frame. The moment right there is 0. The moment right here is going to be this number. This is M at the 4 foot mark. It's going to be a negative something. And then it's going to have a moment like that. And then it's going to have a moment like that. We're going to have 4 values. 1, 2, 3, 4. To get the next one, you'll draw this. This will still be 3 kips per foot. This will be 1 kip per foot. This will be a triangle. You break it up into 2 pieces. Here's your beam. Here is the bending moment at the 8 foot mark. And this will be 8 feet long. And you'll do the same thing. And you'll tell me this number right here. You're not Getman. But that's okay, you're not Baker. What do I bother with this thing for? Getman? What is the moment right here? You sit in Getman's place, you get Getman's questions. What do I got down here? Yeah. I'm sorry? Yeah, that's your question. Take a look at how high is the load? Hint, hint. How high? That's 12 feet, right. Okay, that's 3 times what? Cut in half. That's 3 times 6. That's 18. And so that load goes right here. So that 18 kips is multiplied times 2/3 of 12. And that's 18 times 8. What's 18 times 8? Good Lord. I think he told me an answer. Well, your mother must have beat you mercilessly. I didn't. I learned my multiplication tables up through 6 by 6. Did you see what he did? In other words, to get the moment of the base, he had the easiest one. He didn't have to break it up into 2 little pieces like you and I did. I asked him for the moment of the base. It's 6 times 12, cut in half, times the moment arm, 8 feet. And that's this moment right here. And that gives us this number we need and this number we need for use in this volume integral table. Now, it's my guess that the guy who was in my office saying, do you not know how to integrate it? And I looked at him, I said, yeah, I know how, I just choose not to. And he said, yeah. Well, my guess is probably integrating might be an easier way to get the deflections we're talking about on this one.
So the fact that on the table he has like a concave down.
Doesn't matter. Doesn't matter. Because he hadn't said it's concave down. He just said, I need this value, that value, that value. His only restriction is this 3rd degree. So you're okay. Now on my tables, I tried to emphasize that fact by showing you a parabola and then showing you another parabola where this end was bigger than that end and everything, but it works. It works for anything. All right. Now, this is M due to the real loads. Next, I'm ready to put a number 1 load on the structure. We will be solving for reaction number 1 later on, but right now, as always, I'm just going to put a unit load on there, and then when we put the full load, when we get the full equations going, we'll multiply delta 1 times R1. This will be R2, and this one will be R3. Yes, you can call it M at something, but I'll tell you what, you'll go nuts on these things. That's the number 3 direction, and that's, oh, a doggone it, went right ahead and did it. That's reaction number 3, which happens to be a moment. All right. Page 2. The next thing is our structure with a R1 on it. Here's what it does. Causes the structure to bend, causes the structure to bend, causes the structure to move around. What is this guy's name right here? And I tell you what, probably since we're picking to the right, even if it doesn't go to the right, it doesn't matter. It doesn't matter which way it goes. The way it goes will come out when you solve for it. Let me go back to the original picture. Here's the original picture. What is this deflection right here? What is his name? Delta 2, 0. Well, no, it won't be 0, see, because this is not a real load. This is a unit load. It's a good first guess. This is the deflection in the number 2 direction because you put a load in the number 1 direction. This is the deflection in the number 2 direction. It may be drawn incorrectly. We're not going to use the drawing for plus or minus anyway. You couldn't possibly outguess which way it goes. This is the deflection in the number 2 direction because you put a load in the number 1 direction. What is this number right here? What is this number right here's name? He has a name. You got a name. You want to watch me prove that? Carol? Well, it doesn't matter. I just want to make sure you knew your name. This guy's got a name too. First off, with not much doubt, his name is not Delta. Why? Booth? Because it wasn't caused by a real load, caused by a unit load. It's going to be called by a unit load. We make him properly subservient to us and show him he's a little weenie by using a little delta for him. Now the question is, which direction are we talking about for that deflection? It's the number 1 direction. Who caused it? That's right. That's his name. And I tell you why it's important you know what these things are, because you're going to have to go find a moment diagram due to a unit load in the 1 direction with a 1 kip real load in the 1 direction to get this guy's value. And finally, we have this right here. I have no idea if it really rolls that way or not, and I don't care. And his name is the deflection in the number 3 rolling direction because somebody messed around and put a unit load in the number 1 direction. And it will have a moment diagram because of that load. Kruger, how much moment is there in the frame? And the Kruger, is it still 0? It's not now, right? All right, so here's the moment diagram. Now then, we said that the moments would be positive if they caused compression on the outside of the frame. All right? So that's right. This will be a negative. Now, I don't care where you plot it, but I do care what you label the moment. That is pulling down. It's causing tension on the outside of the frame. This number right here is 1 times 10, and therefore this is a minus 10 for the moment. When you go around the corner, if you look at the corner of something, whatever the moment here is, I don't care how big the shear and I don't care how big the axial forces, they're too close to the corner to cause any change. The moment that comes out the other side is the same number. Therefore, I plot a minus 10, and it is constant all the way down to the floor. And that guy's name is M. That's M sub Q. Due to a unit load in direction, well, it's not just M sub Q, is it? It's going to end up being M sub P also. In other words, you remember we said we were going to put a real unit load and then multiply it times R sub 1? but it's due to a load in the number 1 direction. All right, I don't know what else I might need on that page. Let me continue. Here is the structure.
Why are we putting real unit loads?
All right, one of the things that you will be asked to do is to solve for the deflection in these directions due to real unit loads, real 1 kip loads. They don't have to be unit loads. And the reason is you're getting ready to ask me how much this thing deflects down due to R1. And I can go ahead and put R1 on there now. I can change this to the number R1, and it'll go in the equations. But it's usually easier just to put a 1 for now and then multiply it times R sub 1. Correct. All right. Here's the next one. This is either a unit load or a real load. Take your choice, depends on what you're going to be using it for. This will be M sub Q due to a load in the number 2 direction. Sometimes it'll be M sub P due to a load in the 2 direction. I'm going to plot it on the outside just because otherwise it gets all covered up on top of itself. But I'll put the right sign on the moment. That's 1 times 1, 1 times 2, 1 times 4, 1 times 8, 1 times 12. 1 times 12, that's 12 kip feet. The question is, does it cause compression on the outside? Yes, then that should be marked as a plus 12. And if it's on the outside, this will be a plus 12. This will be a plus 12. And as you go around the corner, this will be a plus 12. And as you go down to here, the unit load will be multiplied, or the real load will be multiplied times no moment arm, so it goes back to 0. Here's what the deflected shape looks like. Gonna go like this. Gonna go like this. Gonna go like this. I have no idea what it's going to look like, but I don't care. I mean, you're welcome to say it looks like this. That's okay. As long as you know this guy's name right here is the deflection in the 1 direction due to a unit load in the 1 direction. And this is the deflection in the number 2. All right, now hang on, let me see, go back to my reference here. 1 is vertical. This is the deflection in the 1 direction due to a unit load in the 2 direction. Thank you. This is a deflection in the 2 direction due to a unit load in the 2 direction. And this rotation right here is the deflection in the number 3 direction, 2, 2, 2. This is probably more likely to what it really looks like. That's delta 2, 2. That's delta 1, 2. And this angle right here in radians is delta 3, 2. And we have the moment diagram and the values that goes with it. Incidentally, if you say, I just can't stand that thing there, I can live with that for the unit load, but I think you ought to put R sub 2 there, then scratch that out and put R sub 2, put 12R2, put 12R2. That's okay. And finally, here's the structure. Here is, which way did we call positive? We call the positive reaction this way. This is R sub, oops, I'm not going to put that. I'm going to put a 1. If you don't mind, I'm going to draw it on the outside here, just so it doesn't get all cluttered up in the middle. And I'll put the proper sign on the moment diagram. Some of the moments 1, 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 some of the moments 1. Now then, does this guy cause tension or compression on the outside? Tension, then this is a minus 1, 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 and a minus 1. And this is the M sub Q or the M sub P, whether you figure that as a unit load or whether you figure it's a piece of the reaction number 3, due to loads in the 3 direction. And I think we got everything we need. Here's our job. Our job is to make delta 1 go away by a judicious selection of R sub 1 causing these deflections, and R sub 2 causing these deflections, and R sub 3 causing these deflections. This is delta in the 1 direction because you tinkered around with a number 3 force. This is delta 2 because you tinkered around in the number 3 direction. And this is delta 3 due to 3. Now, it's going to take you a while to absorb this, and if you just walked in, do you have a prayer?
Nope, no prayer.
Probably. That's going to take some thought. Here is my overall equation. The deflection in the number 1 direction, because you put some real loads on a goofy structure that wasn't true, plus the deflection in the number 1 direction due to a unit load in the 1 direction times R1. In other words, this is delta 1 due to a unit load multiplied times R1 will give me the total deflection in the number 1 direction because of this guy, plus the deflection in the number 1 direction because somebody's tinkering in the number 2 direction, R2, plus delta 1, 3, R3 should turn out how big? 0 is correct. Delta 2, 0. plus delta at 2, delta at 2, delta at 2, because you tinkered in the 1 direction, R1, because you tinkered in the 2 direction, R2, because you tinkered in the 3 direction, that big, should be no movement up and down. This is no movement to the right and the left. No, I guess this is up and down. We chose number 1 is down. Yeah, we chose R1 is down. And finally, delta 3, 0 plus delta 3, 1, R1 plus delta 3, 2, R2 plus delta 3, 3, R3 is equal to 0. That says delta 1, 0, delta 2, 0, delta 3, 0. You know what matrices are. Delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, delta 3, 3, times R1, R2, R3 is equal to 0. I'm sorry, tell me that again. That, thank you. I was trying to impress you and just got carried away. That says this plus that times that plus that times that plus that times that is equal to 0. And I don't know if you've done matrices. I don't know if you've had that yet. I guess you probably had it in some math classes. You can invert the matrix. Yes, sir.
What's the interpretation of delta 3?
Delta 3,
Is that,
3?
well, just overall, isn't that theta?
Okay, let's start over. Yeah, that's my point. Tell me your question good and loud.
Just wondering what the physical interpretation of delta 3 is.
All right, this one or this one?
Overall.
I don't know what you mean overall. I can tell you what this is, or I can tell you what that is. But overall, I don't know what that, I really don't know what you're asking.
Maybe he means both.
What does he mean?
Maybe he means both.
Rest. The one calls this one right here. That is the deflection in the number 3 direction because you put some real loads on the structure. That's this number right here. Take the real structure, turn it into a primary structure, put the real load on it, and how much rotation does this end roll? Nobody but Getman. Nobody but Getman. All right. Pop quiz. That's what the Bible says. It says, when one sins, all shall suffer. Give me a primary structure. And indicate delta 1, 0. As soon as you finish the pop quiz, or you don't even have to do it. It's okay with me if you don't. But if you're not already finished, then you're busy asking questions instead of just writing it down and handing in your paper. I don't know. Getman asked that. If you don't know what delta 10 is, so I'm not asking you for it, I just want you to show it to me. Goodness. Here, just bring it up here and I'll put your name on it for you. If you don't have a pencil, we'll bring a blank piece of paper and I'll draw it for you. I'm not talking to you. I'm not talking to you.
Oh, come on.
Pest. Yes, sir. Can I help you
Back to
first?
your office to get the
You
test.
certainly may. May I help you? No, just turn it. Okay. Anybody need any help? What?
I was going to ask if you have the exams.
Yeah, I do.
Yeah, I'm sure I did.
Yeah. Well, I don't know. But I know you didn't come to class to pick it up. I think you did come to class,
Yeah.
didn't you?
Yeah, but
You walked out as
I
soon as
parked
you.
in the loading zone. I stayed there more than 15 minutes. I figure I'd
Yes, sir.
absorb what I can.
Okay. Got a university excuse. It's good for something, sure. Not a university excused absence? Oh, okay. No, that's okay. Yes, sir.
I'm not sure they'll be able to make it to class on Thursday.
What?
My girl was in the hospital.
Oh.
In Houston, so
All right.
I want to go do this. So should I just send you an email or something? Or?
You can, yeah.
Yeah.
But he'll probably raise another ruckus, and I'll probably give another pop quiz. And,
Okay.
all right.
I'll just
But just remind me why the pop quiz occurred, and then I'll give you a makeup.